Hello there. Thank you for watching Differential Questions with Alex. That is me. All right, so again, we're going to continue the idea about second order linear differential equations. And again, we are under the category of homogeneous equations. And specifically, we're going to talk about Wronskian today. So just to give you an outline of where we are with the material. So for this section, it's a very lengthy section, and I split it up into different parts. So this is the main topic, and then we're dealing with homogeneous equations right at the moment. And we've talked about the principal superposition, the linear independence, and then for the linear independence, we had to do a little bit of algebra or trig to figure out if the set of functions were linearly independent. And then we said in the previous video that we need to find an easier way to show that the collection of functions are linearly independent. And so that leads us to the topic about the Wronskian. So just let me give you a sketch of what we have done. On the previous video, we had several examples. The first example had 4 functions, so y1, y2, y3, y4. And then the question was that collection of 4 functions linearly independent? And we said no for the first example, no to the question about linearly independence. Okay. And we saw that y3 was a linear combination of the other ones. So I believe it was y1 plus y2 plus y4. Okay, so if you are able to write down one of the y functions as a linear combination of the other y functions, then this collection of functions is not linearly independent. It is linearly dependent. So that took a little while. Then we had a second example, and let me put that in gray. So we had a second example, but this time we only had 3 functions, y1, y2, y3. And then the question was still the same. Is this collection of 3 functions linearly independent? And then we said that the answer to that was no. Okay. And then separately for the last example, I don't want to go into the details, but for the last example, we only have y1 and y2, and the question was still the same. Are those sets of functions, is this blue set of functions, is that a linearly independent set of solutions, or is it dependent? And for that blue one, I want to recall that the y2, I believe, was 1/2 of the y1. So that was the linear combination. y2 is a combination of the y1. In this case, it's pretty easy, or 1/2 of the y1. But we had to deal with a little bit of trig function there. So we did those 3 examples, and on all those 3 examples, the set of functions was linearly dependent. Linearly dependent. But we want to check whether a set is linearly independent. Okay, linearly independent. That's what we want to check. And then in order to do that, we need something easier to work with. And so that is the topic for today. Just for this video, it's going to be about the Wronskian. All right, so let me give you the definition. So before we move on to the next slide, I want to tell you that in the previous video, we didn't mention anything about the differential equation. So we just said either we have a collection of 2 functions, either we have a collection of 3 functions, or we have a collection of 4 functions. And then we ask individually, is that collection linearly independent or linearly dependent? But we never mentioned anything about differential equations. Now we're going to bring things back to differential equations, and what I want to tell you first is the definition for the Wronskian. Okay. The Wronskian, Wronski was the last name of a guy who came up with this information. Okay, so I need to give you the definition for the Wronskian for 2 functions. Later on, we're going to give you the definition for the Wronskian for a collection of 3 functions. It gets a little bit more lengthy, very lengthy, really fast. But for the only 2 functions, this is your formula for the Wronskian. So Wronskian of the y1 and y2, you have this determinant. So this is a determinant of the matrix, but what we care about is the actual formula, which is here in the double underline. So you have to use the functions, and then you have to use the derivative of the functions. So that's why we have to say that the derivatives, they have to exist. You have to be able to differentiate the functions y1 and y2. All right, so now we're going to go back to the situation of differential equations. Okay, so what we're saying here is that with the theorem, what we're saying is this: suppose that the y1 and the y2 are solutions to the differential equation. Okay, suppose that to the homogeneous differential equation. So suppose you know that. Okay. Now, in order for us to check that the set y1 together with y2, for this set to be linearly independent, all we have to check is that this Wronskian is not 0 for all the x's in the specific interval. That's all we have to check. Yeah. So as soon as we calculate the Wronskian, and if the Wronskian is not 0, then we can say that the set is linearly independent. That's what the power of the theorem is. Okay. So let me give you an example to see how to use the theorem. Okay. So we want to determine whether the collection of y1 and y2, we want to know whether this collection is linearly independent. And you can kind of look at the formula and you can kind of guess that the answer is that the set y1, y2 is linearly independent. Okay, but suppose that you don't know, and so we're going to rely on the theorem. And notice here that I don't even have a differential equation here in this problem. Okay, so the idea about linear independence is not really exactly related to a differential equation. Here, this is just purely algebra. We want to know whether these two functions are linearly independent or dependent. So what we're going to do is we're going to calculate the Wronskian. And so the Wronskian of the two functions is the following. So you can write down the determinant of the matrix. So y1, y2, and then you have to differentiate the two functions. But the formula that we care about is you cross multiply. So y1, y2 prime. So let me just show you. Let me write down the formula first, and then I'll explain where the numbers are coming from. All right. So the red part is coming from multiplying those two guys, and then the blue part is coming from multiplying those two guys. Okay, and then we put a minus in between. So make sure that you put a minus in between. So that is the formula for the determinant of a matrix. But if you don't know anything about matrix, it's perfectly fine. Here's the formula. Okay, here's the formula that we're going to use. And so in order to do that, we do need to know the functions, and we also need to know their derivatives. And so the derivative of x is 1. The derivative of x squared is 2x. And now we're going to use the formula. And so y1 is x, the y2 prime is 2x, minus y2, which is x squared, multiplied by the y1 derivative, which is 1. And so now this simplifies to what? So this is 2x squared minus x squared. And so this is equal to x squared. Okay. And so do you remember that the condition was that the Wronskian, so let me write this down on the top. So the Wronskian of the y1, y2 is not equal to 0 for all x, okay, for all x in the specific interval. So this last notation just means that for all x in the specific interval. And so here I didn't give you a specific interval because I want to talk about it here. Okay, so we have this Wronskian, and then we calculated the Wronskian of the y1, y2 is equal to this x squared. Okay, and then we don't want this Wronskian to be 0. Okay, so when is this Wronskian equal to 0? This is equal to 0. So this is equal to 0 when x is equal to 0. Okay, so what that means is the following: the interval in the very beginning, well, whatever the interval you have, as long as it does not contain the 0, you're good to go. So let's say 1, 3. If you have the specific interval 1, 3, since the x equal to 0 is not in the interval 1, 3, then this Wronskian is not 0 on the interval 1, 3, and so you're good to go. Meaning that the functions y1, y2 are linearly independent on the interval 1, 3. Right. So what I'm trying to emphasize here is that the interval is very important. It might seem like just like a extra thing to put in there, and just some numbers, some random numbers to put in there, but it actually does make a big difference in the mathematics. Okay. So if we make the interval to be 1, 3, then these two functions y1, y2 are linearly independent. Okay. What about if the interval contains 0? then that's a different story. It means that we cannot use the theorem. It doesn't mean that the functions are linearly dependent. It just means that we cannot use the theorem. All right, so let me go back to the theorem to show you what I was saying here. So we had the y1 and the y2 solutions to the differential equation, but it doesn't matter that they are solutions. We have a collection of two functions, and then if the Wronskian of the two functions is not 0 for all the x's in the specific interval, then we can say that the two functions are linearly independent. That's what the theorem is saying. So notice that the interval is very important. Sometimes a lot of people just ignore the interval and they just work with everything, but they ignore the interval. But I'm trying to emphasize that it is important. All right, so now let's go to another example. Okay, so we actually did this example in the previous problem, in the previous video. We already showed that these are linearly dependent. Okay, but now suppose that you want to calculate the Wronskian for this guy. So what would you have to do? So Wronskian of the y1, y2. This is going to give you, so first you have to plug in the function sine 2x, okay? And then also your function sine x cosine x. But now, what is the derivative of sine 2x? It's going to be 2 cosine 2x. And then you write down sine x cosine x. The derivative of this will be the first function times the derivative of the second one, which is negative sine of x, plus the second function times the derivative of the first, which is cosine of x. So you have to do a little bit of calculus here, and what we now need to do is we need to cross multiply, but then we subtract the two things that we cross multiply. All right, and then when we do that, let me just do the calculation here. Then I'll get sine 2x multiplied by negative sine square x plus cosine square x, and then there's a minus sign. Now we're gonna multiply sine x cosine x multiplied by 2 cosine 2x. Okay. All right, so now here comes a little bit of a trig here. So we still have to do a little bit of some trig identity. The negative sine square plus cosine square, the negative sine square plus cosine square, this is equal to cosine 2x. Okay. That is equal to cosine 2x. And now here on the other side, we have sine x cosine x, that is equal to 1/2 sine 2x multiplied by 2 cosine 2x. And then at the end of the day, this will be equal to 0. You'll see that you can cancel everything out. Okay, the 2's cancel out, and then sine, cosine, on the two terms, they cancel out. So what does that mean? Okay, so that means that y1, y2 are linearly dependent. Okay, linearly dependent. The Wronskian is always equal to 0. So linearly dependent. All right, so the calculation takes a while to do, okay, and then we have to do a little bit of calculus, and then a little bit of a trig algebra, and then we can answer the question. But this is actually better than trying to look at the formulas that we had last time in the previous video. All right, so another example, same question as before, a different differential equation, and we have the y1 and the y2 functions, and then we want to know whether those two functions are linearly independent or dependent. So let me just calculate the Wronskian here for you. So this is just several examples just to get comfortable with the idea. So we have the functions, so e to the negative 3x, and then the derivatives, 3e to the 3x and minus 3e to the negative 3x. Then we have to cross multiply. So let me just write it out. So this is negative 3. Let me just write it out. Okay, multiply by this by negative 3x minus, and then 3e to the negative 3x multiplied by e to the 3x. Okay. So the exponentials, they cancel out. If you have the same base, different powers, you add the powers, and then you will see that it gives you 0. But e to the 0 is 1. So this is negative 3 minus 3, and so this gives you negative 6, which means that this is never equal to 0. So -6 is never equal to 0. And so what we're saying is that the Wronskian of those two functions is never equal to 0. And it doesn't matter what the interval is. What we're saying is that the functions y1, y2, so y1, y2, this collection of functions is linearly independent. Linearly independent. Li for linearly independent. All right, so sometimes the calculation is not too difficult, but at least it has a method to be able to answer the question. We were asked, are the two functions linearly independent or dependent? So if the Wronskian is never equal to 0, then the collection of y1, y2 is linearly independent. All right, so now let me give you just a little bit more definition going back to the differential equation. Remember, we're dealing with a homogeneous differential equation. And so far, we have talked about y1, y2 being solutions, but now we're going to add a little bit to the story. So previously, we said that the y1, y2 were solutions to the differential equation. Now we're adding the adjective of linearly independent solutions. Okay, so do you see that we're adding more to the definition? So we're saying that if the y1, y2 are individually solutions to the differential equation, the homogeneous differential equation, and also if the collection y1, y2 is a linearly independent set, then we call that set a fundamental set of solutions. Okay. So like I said, this first section is an introduction to second order linear differential equations, but we have a lot of terminology, and so I'm trying to break it down as much as possible, and that way we see the stages. Okay, so we talked about solutions. Now we talked about linearly independent solutions, and if we do have those two adjectives, then we say that the collection y1 and y2 is a fundamental set of solutions of the differential equation on the specific interval I. All right, so now question, kind of like reviewing the terminology. Is the pair y1 comma y2, is this set of two functions a fundamental set of solutions to the differential equation? So first of all, are y1 and y2 solutions? So that's the question, solutions to the differential equation? And then the answer is yes. I believe we did this before, but you can check that they are solutions. Okay, so y1 and y2 are solutions to the differential equation. So that's a yes. Secondly, is the collection y1 comma y2, is this linearly independent? Is this collection linearly independent? So independent, I won't write the whole word, but you can see what I'm trying to say. And then the answer is yes. The set y1 and y2 is linearly independent, and you can check that by using the Wronskian. And so if we say yes to those two parts, then we can say that the collection y1, y2 is a fundamental set of solutions. So a mouthful, but once you get the hang of it, you can say this over and over easily. Okay, so the answer basically is yes. All right, so like I said, I want to kind of summarize the main thing here. Okay, so we have two definitions, let's say. The first definition is about solutions. What do we mean by a function to be a solution to the differential equation? We covered that before. Secondly, we talked about the idea of the set y1, y2 to be linearly independent. The easiest way to check linearly independence is using the Wronskian. And you can check that, and then this will be a yes for part 2. If you have yes to those two parts, then you can say that the set y1, y2 is a fundamental set of solutions to the differential equation on the specific interval. All right, so just a little bit more terminology here. Okay. So the general solution to the second order homogeneous linear differential equation with the fundamental set of solution is given by the following. So it's a mouthful. Okay. It's a mouthful. Okay. So general solution means this thing on the bottom. So we have the differential equation, and then we're saying what is the general solution to the differential equation, or what do we mean by the general solution to the homogeneous differential equation? And what we mean is this linear combination. But this linear combination, the y1 and the y2 has to be a fundamental set of solutions. That's the catch. Okay. Right. So it's a lot of terminology, a lot of words, but I hope that you can see that we start with a differential question, and then we first want to know, does this differential question, can we figure out two solutions to this second order differential question? Then we have to figure out whether the set of 1, 1, y2 is linearly independent. If they are, then we say that the fundamental set of solution, well, we say that this is a fundamental set of solutions. Once we say that, well, then we go back to the differential equation and say, well, the general solution to the differential equation, to the homogeneous differential equation, is given by this linear combination. All right. Okay, so now we're gonna move up a level. Okay, so before we were dealing with a second order linear differential equation. Now in this slide, I want to talk about a third order linear differential equation. And then what that means is the following. We previously dealt with this guy here, so this equal to 0. But now we want to talk about what if we have a third derivative also in our differential equation. So this d function, this is just a function which I'm just calling d. That becomes the important parts. Before, the a was the important function. Now the d is the important function. But in any case, going down to the theorem, we're saying that suppose that we find three functions, suppose that we are given that these three functions are solutions to the differential equation, and then we want to know whether they are linearly independent. Okay, so we want to know whether this set is a linearly independent set. And so what we need to do is we need to check that the Wronskian is not equal to 0 for all x's in the specific interval. But now this is a Wronskian of three functions. And then the Wronskian of three functions is still a determinant, but the formula becomes this very lengthy thing here. Okay, so I do have an example, and what I've done is I typed up all the formulas into little pieces, and that way it's manageable to read. But still, the same idea as before, we want to talk about linear independence. Okay, so we have this third order linear differential equation, and then we are saying, well, this differential equation, the solutions to this differential equation, we have three of them. So y1, y2, y3. We haven't said how to get them. That is actually what we're going to do in this chapter. But right now we're just trying to get the terminology. So we have three solutions to the third order linear differential equation. Now we want to know, is this collection of three functions, is this a fundamental set of solutions? What does it mean for the collection to be a fundamental set of solutions? First of all, each one of them has to be a solution to the differential equation. So I'm already telling you that they are solutions. You can check if you wanted to. The other thing that we need to check is that the collection y1, y2, y3, the collection has to be linearly independent. How can we check linearly independence for three functions? Well, we use the Wronskian. And this is the formula for the Wronskian. So I typed it up here again for you. And again, here, this just means that we have, this means, it means the first derivative, second derivative, first derivative, second derivative of the specific function, either the y1, the y2, or the y3. It gets really messy, but this is the formula. And we do want to memorize it because we use it over and over again. Now, with the specific functions that we have, the y1, the y2, and the y3, this is what we get. Okay, so let me just give you the big picture here. So y1 is here, y2 is there, y3 is there. So you can double check that I'm putting the correct information. So the derivative of y2 is this guy. Okay, the second derivative of y3 is this guy. The first derivative of y3 is this guy. The second derivative of y2 is this guy. All right, so that's color coding. You can double check later on that these are the correct things. And now let me choose a different color. Let me choose purple. So the derivative of y1 is itself. The derivative of y3, second derivative of y3 is this guy. The first derivative of y3 is this guy. The second derivative of y1 it's itself. All right, so you can check the other ones. I'm just telling you that we have this very lengthy formula, and all we do is we plug in the correct derivatives or function inside. Then the thing that we have to do is we have to simplify this. So I simplified the square brackets, and so I got those square brackets a little bit simplified, and then you can actually combine them. Okay, you can combine them, and then you get the following. Okay, so you get, and also what I'm doing here also is a 5x multiplied by e to the x gives you 6x, and that's true for all the other terms also. But you can look from the formula here that the first two terms cancel out, and then you get 2e raised to the 6x. And then this will never be equal to 0 for any x. Okay, so this is an exponential function. This exponential function will never be equal to 0 for all x's. Okay, so it doesn't matter what the interval is, but this Wronskian, the Wronskian that we just calculated here, this is never equal to 0. So what does that tell us about the collection of three functions, y1, y2, y3? What does this tell us about these three functions? It means that they are linearly independent. Okay, so linearly independent, and then we just said that they are solutions. Okay, so if you know that the three functions are solutions and that they are linearly independent, then you can conclude that the collection is a fundamental set of solutions. So a lot of terminology, at least three terminology here: solutions, linearly independent, then the fundamental set of solutions. All right, so now let's go to the next slide. Okay, so now just repeating the terminology or trying to emphasize the terminology here. We just finished the problem about saying that the y1, y2, y3 is a fundamental set of solutions. That's what we said in the previous slide. Now this question is asking us, what is the general solution to the homogeneous differential equation? What is the general solution to the differential equation? And so the general solution is going to be the linear combination of those three functions. So c1 y1 plus c2 y2 plus c3 y3. So this is the general solution, which is, with the formulas, this becomes e to the x plus c2 e to the 2x plus c3 e to the 3x. And then the 1, 2, and 3s, this problem I just chose it because it's a little easier to present. But the 2 here has nothing to do with the 2x here, and then the 3 here has nothing to do with the 3x here. So you can flip-flop the functions or the numbers c1, c2, c3, and it's still perfectly fine to write that down. All right, so this is your general solution to the homogeneous differential equation. And again, here we have c1, c2, c3. These are called the parameters. So we have three parameters, and we are free to choose any value for c1, c2, c3. So the general solution is not just one function. This is not just one function. Since we have infinitely many choices for c1, infinitely choices for c2, and infinitely many choices for c3, that means that we have infinitely many choices for the solution to this differential equation. And connecting back to the existence uniqueness, okay, going back to the first topic about this section about existence uniqueness, here I did not write down an initial condition. Okay, so we just only have the differential equation, no initial condition. So whenever you have only the differential equation, then you have what we call the general solution. All right, so I have one more slide. Actually, I don't have any more slides. The other slide is just an outline of what we are dealing with. Okay. Okay. So that's all I have for today. Okay. So this presentation is about the Wronskian, and the Wronskian, we use the Wronskian to figure out whether a set is linearly independent. Then, if we know that the functions y1, y2, y3, for example, are linearly independent and that they are solutions to a differential equation, then we say that the collection is a fundamental set of solutions. Then, once we know that, then we can write down the general solution to the homogeneous differential equation. All right, so that's all I have for today. I'll see you next time.